This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, and we're at Lecture 22, Part 1 of a two-part series on sputter deposition. Our reading is the second half of Chapter 12 in our textbook by Campbell. We talked about, in the last two lectures, evaporation as a technique for depositing mostly metals, but also a few dielectrics onto wafers. That technique is not as commonly used today because we have a better alternative, and that better alternative is sputtering, or sputter deposition. Sputtering largely solves the problems that we saw with evaporation, problems of uniformity, of control, of quality of films, and it has now become the dominant technique for most metal deposition, and some dielectrics as well. There's some metals like tungsten that we often deposit with CVD. Copper is deposited with electrochemical deposition. But for most of the other metals, sputtering is the preferred dielectrics as well.
It's the system that we use for sputtering, which we'll see in the next slide, is similar to the systems used in some plasma etch applications. In particular, parallel plate plasma etch systems. We're going to talk about that later, but when we get to that subject, you'll probably find what we'll discover here about sputtering is very similar to what we'll learn about plasma etching. In the plasma etch system, we etch the wafer, and here we're going to etch a target with the material we want to deposit on it, rather than the wafer. So let's look at a sputtering system. Sputtering system I'm showing here is the simplest form. It's two parallel plates that we apply a voltage across. The cathode is the target. So this is made of the material that I want to deposit on the wafer. I'm going to put in a gas, an inert gas. Argon is almost always used. And in this inert gas will form a plasma. The plasma will sputter off the metal from the target, which will then float around, and some of it will land on the wafer, thus depositing the material on the wafer. We'll create a voltage difference between the argon gas and the cathode, which is the target, and that is what will cause the sputtering to occur. The cathode is generally cooled because this sputtering does generate heat. And the anode could be either, where the wafer is sitting, the anode can be either heated or cooled depending on what we want to do. Let's look at this process of sputtering in a little bit more detail. Our sputtering system begins with the argon as the gas. We specifically choose an inert gas because we want this to be a physical process, not a chemical process. So this is a part of the category of deposition called PVD, physical vapor deposition. So the argon, we'll ionize it so that we can accelerate it towards the cathode, but it's chemically inert. We'll talk about what that means for the sputter yield a little bit later. Then we're going to ionize this argon and create a plasma. Remember, the definition of a plasma is a gas of ions. So we'll use some power source. It could be DC power, which is preferred for most metal deposition applications, or an RF, radio frequency power source, which turns out to be valuable for dielectrics, and we'll create a plasma, a gas of ionized argon. We'll put a negative voltage then on the cathode, the target, with the material that we want to deposit, so that the ionized argon is accelerated towards that target. Slams into the target at the proper energy, we can sputter off bits of that target. The sputtered target material then just floats around in the gas and randomly lands anywhere, and if it lands on the wafer, it can stick and form the layer we're trying to deposit.
Now, one of the key factors, as we saw in evaporation, is the pressure that we keep in the chamber. Now, pressure, in this case, will have two effects. The deposition rate, it will be mostly a function of the sputtering rate. How fast do we sputter off material from the target? And the sputter rate will be a function of how much argon gas is there, because that's the thing that's doing the sputtering, the argon ions in particular. The more argon ions there are, the more sputtering we can get. So we need a reasonable pressure of argon gas in order to have enough ions to get a reasonable deposition rate. But as we saw in our discussion of evaporation, pressure also impacts the mean free path. The resulting mean free path for a pressure of about 1/10 of a torr, or about 10 to the minus 4 atmospheres, is a mean free path on the order of a millimeter. Half a millimeter calculated for this particular case, but on that order. That means distances from target to the wafer being much larger than this mean free path, we will have many, many collisions of the sputtered material as it travels from the target to the wafer. These many, many collisions then will result in material arriving at the wafer at a random angle. Every time we have a collision, the target material will bounce off in some arbitrary direction, and with many collisions we'll end up with all kinds of angles arriving at the wafer. What does that mean? Well, it's not line of sight deposition like we had with evaporation. Instead, this more uniform range of angles means that we'll often get target atoms striking the sidewall at near normal incidence, just like it might strike the bottom of a hole or the top of a material, top of the wafer, at near normal incidence. Material arrives at all angles. The result is good step coverage. Now, that can be a good thing or a bad thing, depends on what you want. But if you want good step coverage, we can achieve it with sputtering. There's still some shadowing. A flat place on the wafer will see a range of angles from plus to minus 180 degrees, plus to minus 90. But a sidewall will only see half of that range of angles hitting the sidewall. As a result, we still don't get perfect step coverage. We still get some shadowing, but it's better than evaporation, a line of sight style of deposition. And the key is the pressure being large enough to make the mean free path small compared to the target to wafer distance. Another important parameter to think about in terms of sputter deposition is the sputter yield. Sputter yield is defined as the ratio of the number of target atoms released per argon ion hitting that target. So you might imagine not every argon ion would be successful at releasing a target atom, or possibly one high energy argon ion hitting the substrate might knock off 2 or 3 target atoms. So the yield is the average number of target atoms released per argon ion hitting the target. Now, the yield is a very strong function of the ion energy. If the ion energy is very low, well, it's just not enough energy to knock off a target atom. Typically, ion energies below 10, 20, 30, a few tens of EVs might not be enough to cause any sputtering. There's some threshold energy required, and it's usually in the few tens of EV. Below that, the yield is 0. Likewise, if the ion energy is too large, bigger than a few keV, something like 10 keV, instead of sputtering, we get ion implantation. Just like we saw when we looked at ion implantation, if you strike an ion into a substrate, with high enough energy, you'll get implantation. Implantation is not sputtering. And so our sputter yield goes to 0 at too large of an energy. Well, if sputter yield is 0 at low energies and 0 at high energies, there's going to be some energy in the middle that maximizes the sputter yield. So we will try to find the optimum ion energy that maximizes the sputter yield, and we try to get yields bigger than 1. It's hard to get a yield bigger than 2, but usually we can get something between 1 and 2 depending on the target by optimizing the ion energy. Well, throughput will be a function of the sputter yield. The higher the sputter yield, the greater the throughput, the deposition rate of the system. But there's something else that will affect the deposition rate. The yield multiplied by the density of ions, that is the flux of ions rather, not density, the flux. The flux of ions hitting the target multiplied by the yield will be the flux of target atoms released from the target. So we want to increase the sputter yield to be as high as possible, but we also want to maximize the flux of ions hitting the target. Well, how can we do that? One way is with pressure. Higher pressure, more argon atoms, more argon ions being generated, and therefore faster deposition rates. But there's a problem with too much pressure, too many collisions, etc. Mean free paths become very small. But there's a way to increase ion densities in the plasma without increasing the pressure. And the most popular way of doing that is with something called magnetron sputtering. As the name implies, we add in a magnetic field to our system besides the electric field. So think about parallel plates, anode and cathode, with a voltage difference between them that generates an electric field. And any electrons that we can inject into the system to smash into argon atoms to create argon ions will move according to this electric field. But if we add, in addition to the electric field, we add a magnetic field that's parallel to the wafer and thus perpendicular to the electric field, what's going to happen? Well, we're going to get an electron that moves not in a straight line but in a spiral. Recall when we looked at mass analyzers in ion implantation that the magnetic field acting on a moving charge will produce a force equal to the charge times V cross B. So the faster the velocity of the electron, this cross product will create more of a force, and the result will be an electron that moves in a curved path. But we also have the electric field present as well, which we didn't have in the mass analyzer of our ion implantation system, only a magnetic field there. But now we have an electric field which is adding its own force. That force will be straight up and down. The magnetic field crossed with the velocity will give me a force that's always perpendicular to the path that the electron is flowing in. The result, when I add these two forces together, will be a spiral motion. All right, if I didn't have the electric field, I'd get a circular motion. I add the electric field in, I get a spiral motion. So it just spirals up instead of going in a straight line. Well, that's a much longer path length. Much longer path length means a much higher probability of finding a much higher probability of slamming into an argon atom and creating an argon ion. This results in a higher density plasma. And that's our goal, to increase the density of the argon ions, which will increase the number of target atoms sputtered for a given sputter yield. And faster deposition rates. Magnetron sputtering has become quite popular today for its higher deposition rates. So, what have we learned so far in our first lecture of our two-part series on sputtering? Well, you should be able to, after listening to this video lecture, describe the basic components of a sputter system. how is good step coverage achieved in a sputtering system? Compare that to what we achieve in an evaporation system, for example. Define sputter yield. Explain the operation and the effects of magnetron sputtering.